be presenting the talk today on building reasonable expression DSL with Kleisli. Now,
Right?
yeah.
Looks like the people in the back cannot hear you still.
Oh, okay. Let me.
Is that
Close it a little lower.
Maybe, yeah. I noticed it just kind of wasn't picking me up. Seems very directional.
maybe I can increase this here?
Actually, that would be helpful, yeah. Testing. Oh, perfect. Alright. Pardon the rough one there. Okay. Okay, so that's working now. So, I'm just curious, before we begin, can I have a show of hands of folks that are familiar with Scala Z? Okay, cool. And how many people know what a monad is? Okay, cool. All right. Now for those that didn't raise their hand, that's perfectly fine. I'll be given like an introduction in those areas, so bring everybody sort of on the same platform there. So yes, today we're going to be talking about building a reasonable expression DSL using Kleisli, and Kleisli is going to be sort of the star of the show, if you will, but we will be talking about other category theory concepts using Scala Z code examples. I should probably give a quick intro of myself. So I actually work at Verizon as a part of the OnQ team, which if folks may have heard the history, OnQ started at Intel as Intel Media, and then Verizon purchased OnQ, and now that's under Verizon. And we work on a video platform, which actually, those of you might have seen the Go90 mobile application that was released that actually uses the services that we work on. And we're a team of pretty much all Scala engineers, and some client developers as well. So yeah, we actually use a lot of Scala at Verizon, and this talk is actually inspired by some work that I've done there very recently. And so let's just jump right in. So when I talk about building an expression DSL, we'll be talking about building a DSL for defining these expressions. But what I mean by an expression is that you have some expression which represents all sort of composition of multiple operations, and given the provided input, you will always see the same result. And this is regardless of where it is within your code and the sources where the data is being received from. We'll be getting into that in a second. So that's what I mean by reasonable, in that it makes it so as you're building your expressions, no matter how you use them, there's not going to be any side effect behavior. It's always just the result that you get, and that's the end of the story. So if let's say you have like a set of adapters. Now, by adapter, I mean some kind of a data source. It could be from a database, an API, a file written out on disk. And it's possible, when I say adapter 0, 1, adapter I, they all could be the same adapter. The point is that they don't have to be. They could be different data sources where this information is retrieved from. Now, this is a notational convenience I'm using here. I'm not saying that the adapter is taking as input a value and outputting the value right back. What I mean here is I'm saying, okay, we have adapter 0 is returning the value Shostakovich as a string, or adapter 1 is returning a 5. That's what I mean here. So an example expression would be as you'd expect out of any kind of that you'd see any math textbook, where you have arithmetic operations, relational operators, equality, inequality. This would be an example expression right here. You have like say length, which could be seen as a unary operator. Of course, a lot of languages will refer to that as like a function, or if you want to go further back, procedure. But this case here, we're looking at these as operators. Now, we also have to handle error conditions. So, once again, as I said, adapters are retrieving data from various sources, and they could blow up in many surprising ways. So we have adapter 0 is returning an error, adapter 1 is, or I should just say, throwing an error, and, well, adapter 2 is behaving, but it doesn't really matter because when you're trying to compose this expression together, you have a few of the operators are returning, or a few of the sources are returning errors. Then what we really want to do is we want to short circuit those that are returning correct values and just simply return a combination of all the errors in the result. It's also possible we can have operators that may generate errors themselves, with division by 0 being the classic example here. So we're going to be building a library that takes all this into account, that allows us to construct expressions with arbitrary operators, or I should say arbitrary expressions, using a library of operations, and be completely agnostic of where this data is coming from, be able to support operators that are both binary and unary, 1 versus 2 operands. We could extend this to Unary operators, but for the purposes of this talk, we'll be talking about a sort of a more basic operation library. And error handling is going to be key here, because for folks who may have tried written their own expression language, it's easy for error handling to get out of hand and get really difficult to manage. So what we're going to be looking at is a way of isolating that from the rest of your logic, so that it's a lot easier to add new operations to your operation library, and to make some changes to how you're handling errors, so they're independently of each other. So, and yeah, it's pretty much redundant. So now what we want to do is we're going to be using the tools of category theory, and you can think of what we're trying to do here is gathering all the values from the adapters and generating a result from that. So let's take a look at a very simple expression language, or I should say an example program or example expression written in this language. So we have x to the power of n plus y to the power of n, triple equals, because remember these are our own DSL operators, z to the power of n, and so you have a Boolean operator, n is greater than 2. Now, these symbols that we're using right here, when I say symbols, I'm referring to these right here, where you have a single quote in the beginning. That for those who haven't seen this used in Scala before, it's really like a string, but they're often used as IDs, identifiers. It sort of reads better, and it's just kind of an extra notational thing. I believe they're in turn strings too, so it's going to be a little bit more efficient. So that will be your expression, and your input in this simple language. We're not going to be reading from a database or reading from an API, although you certainly could. We're just going to make this simple, so if your input's just a map, and you can evaluate it like so down there. So just does this jump out? Does reading this, does anyone have an idea what value the result will be? Because it's always going to be the same value.
False.
Sorry?
False.
Who said where? Yep. Why?
It was proven in 1998. Right?
Yep, Andrew Wiles.
Andrew Wiles.
Yep. Yeah, Fermat's last theorem says that will never be true. So.
So you're putting theorem prover in here too to optimize?
No, that'd be pretty. Yeah, that would be a much longer talk, I think. So let's back up a little bit and look at a few things that most of you might have seen before at some point. This is really sort of fundamental higher order. Perform right there would be probably the simplest form of a higher order function, where you pass it a function, you pass it a value, and you apply that function to the value, and you get your result. So we have a few functions here. We have bump and split, where you're increasing the value by 1 and dividing it by 2 respectively. So we can compose them together either using compose or and then. You'll notice the order's reversed there, but they achieve the exact same thing. Compose would be more like mathematical terminology, where you're saying that, okay, you have your split operation, and then outside of that you have bump being applied to that. Whereas you have and then, which is saying, okay, well, you're splitting it first, and then you're bumping the value. They both mean exactly the same thing, but the principle there is you can define functions, compose them together, and essentially by doing that, you can have more than 2 functions. You have a whole library of functions, and you can combine them in various ways and build expressions that way. The problem is there's no real guarantees on the values on the right side, which would be in math terminology, Codomain, of your answer. It's of your result. There's no real guarantees on that value at all. It could be any value. So if you combine these functions together in various ways, well, it's kind of left up to you to make sure that this composition actually makes sense. There's no real extra machinery there to make that go more smoothly. And the main vehicle by which we achieve composition is a concept in category theory known as the monad. Now, this is actually taken from the Scala Bay library. So that's why if you're familiar with the Scala Bay code base, you might say, hey, that looks familiar. I mean, the variable names are clearly the same. But those same folks will probably notice, hey, there's a lot less methods inside this trait. Well, that's true. If you looked in the Scala Bay library, you see a lot of helper methods that allow you to do different, cool things with monads. But if you want to go down to the actual root mathematical definition of a monad, this is it right here. There's a point method and a bind method. The point method is it's pretty much the same for any kind of monad or collection, which would be a monad. The option monad has a point method where it has a point class with an apply to be, if you want to be really specific with this. But here, the point method allows you to take a value and lift it from its raw type into a monad. So sum 5 would give you an option value containing the number 5. Sequence 5 would give you a sequence which is one element, which would be 5. And this is consistent with all monads. You can lift a value into it using the point method is the way this is achieved. And of course, there's also, this actually goes a little bit beyond the definition of a monad, but you can actually, there's base cases as well where that for an option of int, for example, if the value is none, it's empty. For sequence of int, it's empty if you say sequence open paren close paren. Now bind is a bit more interesting. It actually does 2 things. It does it at the same time. It will map values from some type A to another type B. But in doing so, it lifts these values up into brand new monads and then just flattens them all together. That's why it's called a flat map. Now, a few examples here. You say you have an option right here, and you say flat map You want to flat map it with some of the length. So you know, this is saying that these are string values. Well, if you used a map there instead, you would end up with basically you'd end up with nested options is what would happen. But with the bind operation, it makes it possible to lift these nested operations and merge it so that you actually have you're flattening the values. So as a result, you have sum of 12 as your actual value. For sequences, you'd have 6 and 12 because you know Dimitri is 6 letters, Shostakovich is 12 letters. So you would have, so that would be flattened as well. So flat map, it works the same way across different operations or different types of monads. Now, there's also different monad laws as well. I think to get into talk about different category theory laws, it's starting to get a little bit deeper than I probably would for this talk. But just be aware that those exist. And it's kind of the same idea as like if you say you're overloading hash code in equals and back in Java world. If you have to make sure you have these overloads consistently. It's a similar idea because I mean you can't define monads in strange ways. I mean they have to follow a certain set of laws. So yes, that's the idea of monads. It's about creating a pattern across different types of data so that you can compose them together in the same way. And this is really a key part of what makes pure functional programming, what makes it actually as powerful as it is. So let me illustrate this by showing a really straightforward example here. You have a string type or a value A of type string, AM type option of string, and then we have methods where you have one that takes a string, returns a string, takes a string, returns an option of string. So the way you would actually do a map with these, you know, on AMM, you just say, okay, AMM length. That will work where AM actually contains a value or not. Now, if we were to go back in, you know, to language such as Java, where you don't have an option, maybe Java 8 does. I'm not really sure, to be honest. If you say if A is not equal to null, A.length else null. So here right away you have to the code just reads differently. You're building. You're essentially building at worst a Turing machine in your head as you're reading through the code, and you have to think mutability and then this is a very small example, but all I have to do is add 2 monads right here. You see quite a difference. Say you want to combine AM and BM. Well, you just do a flat map there. That'll work in all cases, AM, BM, having a value or not having a value. Versus this, you say it's on the bottom. It's a really simple case, but you kind of have to read it. I mean, whereas that you can just look at it and instantly know what's going on. Now, these really simple examples, but you can imagine as if you're talking about building a large software application or library, the complexity increasing dramatically, exponentially, so as you have more components. And really, this is really what makes pure functional programming truly powerful, and I would argue even essential. So let's say we have a function from A to M of B. Well, what do I mean by this? Well, I'm saying M is a monad. And I'm saying we have a function where the domain is any value of any type or particular type A, and your result is guaranteed to be a monad with type parameter B. Well, guess what? That's what a Kleisli is. That's all it is. It's a function that has been lifted into a monadic in a monadic context, where you're placing a guarantee on the result value of the function, thus allowing you to compose these together in a more consistent and uniform way. So it's pretty. The type parameters make sense. The first one being the monad and your domain, and then your codomain. Now I have to pay respect to this guy because I mean so monad Kleislis are actually named after Heinrich Kleisli, but he didn't actually invent them themselves. But he did work that was related to type theory, so it certainly was a very it was a good attribution, and yeah, so I just have to throw that up there.
I guess he invented monads, right?
Sorry?
He introduced monads named triples, right?
Triples. Oh, okay. Yeah, I didn't know that actually. That's cool. Yeah. So it definitely does really important work in field of category theory. So let's now jump into defining our expression DSL. So we're defining a special monad for our purposes, and we're calling it a term. And this is the term that you might have seen in a mathematical sense, where it's a terminal value. In particular, it's a value that is either going into a function or going out of the function. So it could be an error condition or an actual value. Excuse me. So the term really it's a quite simple entity. We're defining it. You notice we're defining it with the plus. We're defining covariant here because we want subclasses of it to be subclass of the type parameter inside. So that kind of makes sense. But it contains a value. It can be seen as containing a value, and also there's this diamond operator which I'm defining, and I'm calling it diamond. This is a represent. It's a notational convenience for representing left and right operands. So you have a left operand, diamond, right operand. And you'll find in code example, as I go through the code to the rest of this talk, you'll find that that diamond notation actually helps a lot, readability. I mean, you could have just left it as a tuple of 2. That would have been fine. So we have this particular method here. We're saying, okay, we pass in another term, then so it'll be this term diamond another term, and then your result is going to be, well, it's going to be of type term E diamond F. So there's a convenience there. Now we're defining our term monad, and this becomes important later on because this is saying, okay, we're defining an object implicitly, so that if there's any question anywhere in the code where it's accepting, it's saying, okay, I don't know this thing you're trying to operate on in a monadic way. I don't know if it's a monad or not. Well, this removes all doubt. What this does is it defines point and bind, as I showed before. And you'll see the definitions are pretty simple. Point just defines a new term with a value A. Bind, it just takes in, it takes in term of A. You have a function going from A to term of B, and it just passes, it reaches into the term, pulls out the value, and passes it to the function from A to term of B. That's your bind, which allows you to do flat maps.
Could you explain just briefly why the diamond operator can be used in the declaration of the diamond operator? I'm kind of new to Scala.
Oh yeah,
so visibility works.
So,
like especially in the type, when you have colon term and use it there, how does?
I should point out that I actually this is sort of forward looking. There's a definition where I have diamond defined elsewhere. Yeah, I do. Yeah, in fact, I've defined it as a case class. Yeah, you'll see that, and I think it's actually the next slide. No, it's the one after that. That one? Yeah, there it is. So you'll see it pretty soon. So we're going to find a few terms. Integer term, string term, you can define a Boolean term, complex numbers term, any kind of term that you want to represent your terminal values. And the case class, as we were talking about right there, you could say, okay, you have a value, diamond, another value. It's going to give you a your diamond pair for binary operations. So another interesting preliminary here, but this is actually our first example of actually creating a Kleisli. And it's surprisingly intuitive for what it does. Let's say we have a function lived into a Kleisli, a of m to b, or a to mb, diamond a to mb. So two functions on the left and right side, and the result we want to give is a m b diamond b. This is how you would do that. We'd say, okay, well, let's define implicit class so that we can take any Kleisli and perform this operation between them. On the left side, you would have, okay, term a to b. Then the right side of this diamond, you have term a to b as well. Result, of course, term a to b diamond b. But then right here we say, okay, Kleisli term a b diamond b. We're going to lift this function that takes in a type a and actually returns the value of the left-hand side Kleisli evaluated at a, and also the right-hand side evaluated at a. And then you have your result right there. It's literally that simple. And that can be achieved because Kleislis, remember, they're just functions. They're functions lived in monad form, but they can be evaluated like functions where you can pass a value to it and get the result. Because Kleislis actually have the apply method implemented. That's how that works. So let's define some simple logic operations where.
Ryan, can you go back to the previous slide?
Sorry? Yeah.
Yeah. Just leave it up there for 30 seconds.
Okay.
I don't understand so the case.
Yeah.
The match expression there is the function parameter of the Kleisli. Is that what that is?
That's the input parameter. Because remember, Kleisli is just a function going from domain to codomain, whereas it's type A right here, and then that's your input case A, and then the result has to be a B diamond B. Well, what's the right side of the left-hand side is a B, and also a right, that's a B as well. So if you evaluate it at A as input into both this and that, you're going to get your type that you expect, B diamond B.
Quick question.
Yeah.
Are you calling the apply method in there?
That is exactly. There's apply method on Kleisli.
So
Yeah.
it's not a pattern matching. It's rather handling the case as a function, which is the input construct.
Well, it's a pattern match, and it's also. This is
It's a partial function.
partial function, right? Yeah. That's why. Yeah, that's what I'm looking for. It's a partial function where you're saying, okay, you're satisfying the case where it's A, and then actually evaluating LA diamond RA. Does that make sense, everybody?
Yeah. Do you really need the case in there?
Sorry?
Do you really need the case in there? Maybe you can just remove it.
You can get away with that without it, but that works too.
Actually, that's right. Yeah, you could do without it. Actually, yeah.
You can do without what?
Actually, that's a good point. Yeah, you could take the case out on this.
Yeah.
Yeah.
That's awesome.
Right. Yeah. So you could do that. So this is just a closure is what this is. So that should be fine. Yep. So yeah, let's take some sample operations. I have a few type definitions for convenience. We have a fault, which is an error condition. We have operations with no faults and operations with faults. Now, the difference between those is, in all cases, we're supporting error handling where your sources are returning data. So that's implied. But in terms of defining your library, if you have to define operations that may return errors, like division, for example, if you pass a 0 in the denominator, then that would be an operation with faults. So so when I say with faults versus no faults, it's faults that are generated by the operator themselves, not coming from externally. So operations with no faults, it's a Kleisli where the monad's a term, the input's I, output's O. With faults, input's I, outputs is this interesting thing here, fault, or also known as disjunction O. Now, that is actually a disjunction is another really useful tool in Scala Z. And for folks who know about the Scala Either, this is actually a much more flexible version of the Scala Either. The problem with Scala Either is it's really just kind of it's it could be either this value or that value, but you can't do maps on it, you can't do flat maps on it, because there's no real bias on whether you're talking about the left or right hand side or not. I mean, it could be either one. So you have to have all this conditional logic where, well, if it's the left side, do this, if it's the right side, do this, and before you know it, you have all this branching code, which is kind of missing the point of functional programming. Here, you have a right bias, meaning that if you take a disjunction where you have some value on the left, where it could be a value on the left or a value on the right, you do a map on it or a flat map. What it will do is it's just like, say, an option sum. It's if the value is on the right side, that map will apply to the right side, and you do a map operation. If you have a left side value, it will not apply to it. So it'll just sort of pass right through, if you will. It's just think it was like options, sum versus none. Similar idea. Now, the fact it's right bias is totally convention. It could have made it left bias. It doesn't matter. I mean, it was just sort of there might have been some historical reason behind it. I'm not sure why, but if the advantage of this is now it suddenly becomes a monad where you can do flat maps, you can do maps on it, and since it's right bias, it's very often that the left side will be used to represent error conditions. This is a really nice use for disjunctions. So that's exactly how we're using it here. We're saying, okay, you could have an error or you could have your output value. Now we have binary logic where we're saying, okay, we have a binary operation. So once again, you have the type, diamond, that type. And then, particularly booleans, it's a binary logic. Take two booleans or return a boolean. Not L, that would be our first operator that we're defining here. And it's an operation with no faults. And you can see quite straightforward here. We're just defining a Kleisli. I should mention that boolean term is actually, it's not on the slides. All that is just an object with an apply method that just takes in a value and returns a term of it. So that's one thing to keep in mind, is that when you're lifting a function at Kleisli, remember the return type is always a monad of the value. It's a monad of the type. So when you're lifting this function, your function itself has to be returning that monadic type. That's why I have this Boolean term here as a convenience. And then we just map it to negation. That's a not operation. It's that simple. And same idea right there. We have all the underscores because we know there's apply going on the argument, and then you have like the two left and right arguments added together. And you notice that once again we're not taking into account, we're not even worrying about error conditions coming from the sources. You hear me keep repeating that because I mean that's sort of the beauty of this, is you can define your library operations here. Oh yes.
Just out of curiosity, why do you define type signature with and without faults, right? Because now the without faults one, right?
Yeah.
It's non-monadic, and I guess is the Kleisli going to take care of converting between the two?
They won't in this case.
Okay.
And
you just did it because you're guaranteed there are no faults, and it's a little cleaner than the disjunction? Right. We don't really need the with faults there, that's right. I mean, we're just defining it as a sort of a convenience.
you'll see we have like the division operation. We'll be using that definition there. We're not using it on this slide, but you'll be seeing where we're using both of the definitions. Yeah, but these type definitions are all just purely for convenience. So let's take a few more. Here's a few more operators. We have negation, as you might expect. We have in our type definition. Actually, no, this is not a type definition. This right here is actually it's a definition of a partially applied function, where we say, okay, we have Kleisli there underscore, meaning that we're going to actually apply this. We're going to actually use this apply as a function to other operands, and this would be an arithmetic operation. I'm using E as a type parameter for result for an expression. So you'll see that throughout the slides. We have addition, subtraction, which is kind of interesting in the sense that, well, subtraction is just like addition, except you're just negating the right side. So we do a compose K, which is a function on Kleisli's. We're going to compose with a function. We have division right here, which actually, this is our first case where we're actually using an operation with faults. And what we're doing here is, here we actually have to use a case match in this case, because we're matching the case where you have 0 in the denominator. That's okay, this is divided by 0, this is not a number. We have to return a fault here. We have the general case where, okay, it's fine, you just do a division right there. Now, this is a really neat sort of notational thing with disjunctions, where you have minus v, v minus. And you could probably guess what that means by looking at it. The minus on the left side means, say, okay, well, this is for a value on the left side, it's an air condition. Minus on the right side, it's a value on the right side for right side air condition, or the actual value for the right side. So that returned tells it, okay, which disjunction value side I'm talking about that this value's on. And then we have an exponential operator down there. And same thing goes for comparison operators. You can define comparison operations. You'll notice that I forgot to mention this before. All my operators, I'm actually putting the letter I next to them. Maybe you saw a few D ones. I'm not sure if those are. No, I think they're all integer. The way things are defined here is that the types are specific. They're strictly defined in this DSL. Using type classes, you can actually unify these together, but sort of for simplicity, I've actually defined it this way. I should say maybe simplicity for presenting purposes. So it's possible to unify things. You'll find it's difficult actually to completely unify, and there's actually libraries out there to help you that actually can help you with that. Aside from using type classes, the CATS library, which is an alternative to Scala Z. I'll mention that again later. But CATS is a category theory for Scala. That's sort of like a new, sort of reimagined category theory library. That's more sort of meant as an alternative to use a Scala Z. There's actually a really cool algebra package in there that allows you to unify numeric calculations. I haven't actually used it yet, to be honest, but it looks pretty interesting, so I recommend checking that out. Now, Kleisli is a sort of side note. You can actually use it in place of a dependency injection, particularly in place of the cake pattern. It's a lot simpler to use in that, all you have to do is you could define your Kleisli, and you can think of it as like, okay, I'm injecting my logic in here. That's you could do that if you want, and I could give you an example of a library that's doing that. You take a look at the Funnel project, which we recently open source, in the OnQ team at Verizon. We open source Funnel, which is a monitoring. monitoring library. And this pattern is used a lot in there. We use Kleisli as our return from all kinds of values, and it's amazingly powerful. Now, we're going to jump into the error routing, the error handling part of this. This is a part that I said that we're not going to worry about. Well, now we're going to worry about the error handling, and this is quite interesting. This is actually definitely an interesting part of this, because this is designed, the error handling for this DSL is once again intended not to pollute the rest of your operation library. So you don't have to worry about it when you're defining new operations. So the approach here is, since we're using disjunctions in combination with these Kleislis, I'm going to be showing you a few of the operations for actually handling error routing. And the way it works essentially is, you can think of it as providing sort of this bubble wrap around your functions in your library, where your bare functions don't handle incoming errors at all. But with this, you can pass your library function into this, and it will wrap it with a Kleisli that will take errors in and spit errors back out. So if you have this expression that you're building, and you have errors coming from your adapters, then, well, guess what? They're just going to flow right through your expression. They're going to go, they're actually, you can think of it as sort of a, kind of a conceptual way to think about it, I guess, is that they'll be routed through your expression, so at the end you'll have all the error conditions gathered up. Otherwise, if there are no errors at all, then you'll just have your expressions operate as normally. Now I'll show you what I mean by that. Let's say this particular example is for Unary Operations. Now my symbol name right here, the caret, exclamation, or I don't know, hat, bang, or I don't know what you want to call that. That is actually, what that means is that I have different definitions in here, sort of to be consistent. It's a visual thing, where I'm saying, okay, this is for Unary operations that will not generate their own errors. They may receive some errors coming into it, right? The version of this that may generate errors would be caret, exclamation point, and another caret after it. So it's kind of a visual thing. You'll see how they're used. It kind of makes sense. So let's say we want to define error handling for Unary operators. Well, let's do a type definition. A Unary operator going from A to B. Well, that's in our sort of happy space and defining our libraries, and it's just a value goes from A to B. Well, to handle errors, actually, this could be a non-empty list of errors, or A, coming into the function, or a non-empty list of errors, or B, coming out of the function. All right? Now, non-empty list is a concept in Scala Z that's very, very handy. I'm pretty sure CATS has a definition too. A lot of what I'm saying here, CATS also has these definitions. A non-empty list is, as it sounds, it's a list that's guaranteed to have at least one value in it. And if that doesn't sound very useful, I can give you an example and you'll instantly see why it's useful. Just think of a time where you're calling an API and you get an error conditions, like, oh, there's an error, and you say, okay, what's the list of errors? Oh, it's empty. So that's an ambiguous case there. I mean, you get an empty list of errors. What does it mean? There are no errors, or just the errors are unknown, you just don't know. This makes it clear that it's like you either have a list of some errors or a value. So you pass your operation for the library into this function here, exp, Kleisli term A to B. That's your bare function, doesn't return any errors. And what we're going to do is we're actually going to return a unary through A to B, which is, remember, the version that can have errors coming in or errors coming out. Sort of our wrapper around our library function. Now we do that, we define that by saying, okay, here's our Kleisli, term, non-empty list of false or A, It's a non-empty list of false or B. The input is A, which actually maybe this might be non-empty list of false or A. We take the we do a for comprehension here where we convert that disjunction to an option. And when you do that, if there's a value there, it will be sum of the value. If there's on the right hand side, if there's a left hand side value, which in this case is an error condition, it will just be a none. So in order to actually pass a value to EXP, we want to make sure that the value is actually is valid. It's not an error condition. So then we know, okay, we're going to apply this operation. So we yield the operation. Now we do a result map. That's a case where, okay, there's a value. We map it, and we say, okay, it's a right-hand disjunction of the value. Now, we get the value and convert to a term, but if that was an error condition, we take the A and we do a swap of the left and right side so that the error on the left becomes on the right side, and when you get the head of that, you're actually getting the error. And then now you're turning the error condition. So that handles error routing for unary operators. Yes?
Right, so I see two options here. Two option is a case, so you have this possibly faulty thing, you can convert to option. What would you do if you have an option? Is it possible to convert it like a fault or? It's an empty list of errors, right?
You're talking an option of what?
Well, see, you have this two option method.
Right, yeah.
That's cool because if you have good stuff, you get some. If you have bad stuff, you have an empty, right?
Right, yeah.
None. How about the opposite direction? So you have an option. Can you convert it into this structure?
You convert an option into an option, you're saying?
No, into this like fault or.
So are you saying that A is of type option?
No. No, see,
Yeah.
no, look at this. When we do A to option, right?
Yeah. Mm-hmm.
So we take this A, which may be faulty, right?
Right, yeah.
And transform it either to none or some, right?
Right, yeah.
Okay, but is there an opposite operation? Have an option and transform it into this fault or value.
Are you saying that the op would be an option here?
No, the opposite operation
Yeah?
to two options.
He wants to start with an option and turn
Yeah.
it into a disjunction expression.
Oh, I see what you're saying. Yeah, there is. Yeah, right. There is a symbol for that. It's I'll just do it by hand here. It's like the // greater than. And what that does, if you put it after an option and then you just provide your value there, you're saying that if that option is none, it'll just use that value for the left-hand side. That's what you use. That's very useful, sir. If you're doing like for comprehensions. Very great pattern areas. If you have for comprehensions in a second, if you have for comprehensions where you have a list of options, well, if you're to just have code like this in production and you have one of these just fails out as a none, you don't know which one was none. Whereas if you add that operator was telling you and put strings on those or exceptions, it'll short circuit, but at least it'll short circuit with an error value. Yes?
Can you comment on using disjunction? Why
Yeah.
you use that over validation?
Excellent question. We cover that later on inside the slides. Yeah, but that's a good point. Yeah. I'm showing both to show a comparison between the two because it's interesting to look at. There's some advantages conceptually to using disjunctions, but yeah, validations actually is simpler in a lot of ways. So this makes sense. This is our error handling for a unary operator. Now for a binary operator, now notice it's the caret, bang, caret. This one is for binary operations that may actually return errors as well. And it's very similar to what I showed before. Here, once again, we're saying binary through is, see, we're using a diamond operator. See, if I didn't define a diamond operator, this would be a lot harder to read. So you have non-empty list of faults or left value, diamond, non-empty list of false, or right value. These will operate two operands into the function, and the result, non-empty list of false, or the result. So that's our binary through. So we have a binary operation, let's say it's division. It's passed in as exp. Since it's one of those that may return its own errors, we're saying, okay, it's an operator that has left and right operands, and also the result is false or e, or a value. Now, it's very similar to what we did with the unary operator, but the difference is the for comprehension has two items in it, where we're actually converting two disjunctions to options, left and right. And only if both of them are satisfied, then we could pass it to the function actually operate on them. And that's how we do that right there. The code below it is a little bit more complicated because once again we're dealing with two values. If it's now this is actually quite interesting here because this is only needed for the types to line up, because if you're on the map side, there's no error condition there. But in order for the type correctness there, we're saying, okay, we're mapping that to a non-empty list of the value. So you have a single value and we're actually putting into a non-empty list. Now get or else is if there's an error condition, and then that's where we say, okay, it's a left-hand disjunction, but we're not going to only just swap the left side so we can get the error off of it. We're going to swap the right side too. And we're going to return the list because this could be a list of errors. And we're going to append them all together and reduce them by appending all the errors into one big non-empty list. And then we convert to a term. So very similar conceptually for binary operations. So does that make sense, everybody? Oh, cool. So, all right. So now let's look at an example here where we have, this is kind of a convenience right here actually, and you'll see in the later slides where we're saying, okay, well, an expression where we have input to output is really the same as input to term of non-empty list of false or output. So I define this nice trait here that has the Kleisli inside of it, and that represents the same thing. We use this on further slides. It's a notational thing. And now we're going to reach a point where we're going to start composing these Kleislis together. And just like you saw with regular functions, there's compose and then operators for Kleislis. And there's symbolic forms of these as well. You have and then and compose. And I'll just read you the signature of this, and it'll totally make sense. You have, for Kleisli, we're going from A to M of B. So you want to compose it with another one, which is M, B to C. Well, once you compose them together, you get one M, A to C. That's composition right there. And you notice this implicit type bind. That's actually a super type of monad in Scala Z, and that's the bind operator is what that is. So by defining that monad in scope, you're actually allowing it to be picked up by this parameter right here. Now we're going to start defining our DSL. We've defined sort of the core functionality. We're defining DSL syntax that goes around it. Here we're going to say, okay, we have an integer expression. Takes a Kleisli A of R event R was what I defined earlier, represent possible error condition. So it extends expression A to int. We have negation, different arithmetic operators on it. Also comparison or equality at the bottom. And you see how we're using the Kleisli composition operators going through our error routing operators. So it's really, it's really quite straightforward. I mean, there's a bunch of one-liners at this point. So we're actually really close now. I mean, we've defined our library of operations. We've defined a way to combine them together, handling errors. But all these symbols and maps and this really has no relevance to our to our definition so far. So we kind of have some adapter code that we have to write. And this is, see this, up to this point, everything is very purely functional, strongly typed. Now we're kind of at the edge of our world where we have to interface with outside data. Of course, this is just a simple map, so the worst thing that you'll see here is this a map of a symbol to any. But there's a good explanation, and yeah, that's what I was just saying. So here we have a very simple adapter, where we say, okay, we input our map here, and we actually have a number of conversions out here, such that we say, okay, I want to declare this. I have this symbol. This is an integer. This is a double, or this is a string. And you notice in our example here, we're saying explicitly what our types are. Once again, we're in the world. We don't know what the types of the values are, so you have to. That's where they're defined. So we say as int, as double, as string, and all it does is it accesses a map. Since it's just a simple map, and attempts to do a conversion. Now this is a nice thing in Scala Z. The disjunction either dot from try-catch throwable. That is actually the Scala Z version of a try-catch block. And what that does is that says, okay, anything that's in here might throw an exception, but if it does, well, either way, just give me a disjunction back. So this disjunction will either be valid value on the right or an error on the left-hand side. You'll find out once you start using this, you'll never use try-catch blocks ever again. I don't use them at all. I just use that. It's much nicer to deal with. And I'm doing a left map. A left map is if you want to map the left-hand side, often the error side. And I'm just mapping the exception to get message, mapping it to a string. Now we're going to bind everything together. We have type error indication. We have symbol expressions here where we're saying, okay, if you have a symbol, you could say as and as double as string, and it'll actually create the expressions with the Kleislis defined within them. And we have a convenience here to adapters so that if you're passing to your expression a map, you don't have to wrap it with this adapter. It'll wrap it for you. This right here at the bottom is for constants. So say you have a constant value in your expression. You don't want to have to say, oh, hey, this is an integer. No, it's obviously an integer. I mean, the type system can tell that. So it'll actually convert that to an integer expression for you. And now, after doing all that, this code will actually do as you expect. You can provide any kind of map here. You can have any kind of expression, and it'll just work. And just to give you an idea of as I was building. I mean, this is based on actual part of a system that I've built at Verizon, an actual scripting engine, or you can call it a rule engine. As I was building this thing, given it's a purely functional system, it pretty much worked 100% and 99% once it was implemented. So as I was going, I was doing the different pieces, putting it together. I didn't have to write that many test cases. I just wrote a few expressions. That was enough. And that's really a testament to the fact that you're really using the type system. Everything's completely composable. There's no surprises in the way your code works. You're no longer thinking in terms of all these code paths all over the place. Instead, it becomes mathematical is what it does. So yeah, that'll work. But category 3 being so fun as it is, there's many ways. There's other ways to achieve the same thing, and actually there's something known as a validation applicatives, which was mentioned back there. Think of a validation as in terms of error handling, it's very similar, except that instead of having a left-hand side and right-hand side, you're gathering all your errors together. So if you're to have a disjunction, as I was explaining before, where you actually you have a for comprehension of just disjunctions, and one of these has a error condition, and it just short circuits out. With validations, you can actually gather errors together instead of having a short circuit in the middle. Whichever you want depends on your application. This, for building expressions, it actually makes a lot of sense to use validations. And a validation really is a type of applicative, which that's actually the term that Scala Z refers to. It's really technically called an applicative functor, where a functor supports a map operation. Without getting too deep in the definition of that, I think that would be a great topic for like a later talk. A good way to think of an applicative is a way of doing operations on operands in parallel, so do things in parallel with each other. For validations, it's for gathering errors all together. So these definitions here, just forget the definitions I had in the previous slides. And so for here, I actually have sort of a separate independent set of definitions. We're defining fault again. We say, okay, we're going to have this new thing called an unexpected type. So I'm actually going to start unifying some of the types together. And we have validation NEL. Now, validation NEL is a shorthand for, it's a validation where the error condition is a non-empty list. Since it's so often, it's very common that people use non-empty lists with validations. That's why there's a validation NEL. So that's the same as just saying validation, non-empty list, false, or A. And like disjunctions, left side is like, left side is seen as the error condition, the right side is the actual values. We have an expression definition. We're defining expression a little differently. We're saying expression is simply a Kleisli of term A to B. We're defining the diamond operator a little bit more simply this time, just saying it's a tuple. We have a binary operation, which is just saying, okay, you have your left and right term inside the expression, and going to the actual value to type B. We're going to have a method called lift binary operation where we're saying, okay, I'm going to lift a function, term A, diamond term A, to term B, into a Kleisli of term A, diamond term A to B. Just apply it to this function right here. That'll lift with the binary operation. Now we're gonna go ahead and just define our adapter first, kind of doing things differently in this using applicatives. And we're saying, okay, our source type is a map key to any, and key is gonna be a type string. We have a reader, which actually will read. It'll read any value from the map, the term T, and it does this by saying, okay, get the value, convert it to a string, and convert it to a success NEL, which is saying, okay, I want to wrap this, we'll say that this is a validation where it's successful, and by saying NEL meaning that, well, if it weren't successful, it would be a non-empty list, but it is successful, and it's going to be this value. So it's just to make the type system line up, that's why it's that. And then int reader is for reading an integer. And this parseInt is actually pretty neat. This is built in the Scala Z, where if you actually do a parseInt and it fails, it will actually return a disjunction. So instead of like, oh, it's return exception, got to catch exception, and no, it just returns a disjunction. So it's a lot easier to deal with. So that's your int reader, and we have a wrap NEL, which is kind of the same idea, where you're just saying, well, instead of success or failure NEL, it could be either one, and this just wraps it. Here's what it does. And here's read, which this is generic. So you can see more generic typing in this version I have here, so I'm going to make the types a little bit more generic. Where, okay, we'll take any reader, and what we'll do is we'll get the value from the source. We'll map it using the reader, however reader it gets selected implicitly. And then, well, if we can't find it, field doesn't exist, failure NEL. So this code reads quite easily. Now we're going to find our library. This is sort of an attempt to unify the types of the operations. this is a place where when I was talking about CATS has this algebra library that's something I recommend looking into. I actually have to look into it myself because I think that would actually make this even cleaner. But it's pretty straightforward what we're doing here. We have numeric operations where we're saying, okay, takes in type A and B, and you have add, minus, and division. The reason why we're taking in types A and B is because of the one at the bottom there. You know, you take two integers, you know, you divide them, you know, obviously the result's not, you know, it's, you know, it could be a, you know, a double. So that's what you do is you just say, okay, provide another type for that purpose. That's why there's two types there. Of course, add and minus, we're not counting edge cases where you're like right at the largest possible number and it could numeric overflow. So we're not counting that case, but in general, that's a representing numeric operations. And then we have int operations here. You can do the same for double. And this is really quite neat because we're actually defining this is our validation, applicative notation right here. We're actually saying, okay, we're going to match on case left and right. We're going to take left and right and use this interesting looking operator here, which there's a lot of funny names for it. The Cinnabon operator, the TIE Fighter operator, it kind of looks like a plate with a fork and knife next to it. I don't know, you can call it whatever you want. Home Alone operator, that was the other one. So you can actually, you basically say, okay, you have the left and right side, and I'm going to apply a closure to it where you actually have, okay, the operand and the operator, so it's actually adding these two together like this. Here you're subtracting them, dividing them. That's what that's all about. So that's the applicative notation right there. And this closed division thing is quite interesting because, well, since this could generate an error condition, we're pulling this out as a separate function here. We're saying, okay, well, division is whatever division operator for the types that we're dealing with here. We're going to lift a binary operation. We're going to take the left and right and turn it into a tuple form validation. And then what we do is we match that for, you know, if there's a 0, divide by 0, failure NEL. If it's not, then you actually do the division there. And then you just yield the result there. So that's some extra neat applicative functionality that you have in Scala Z. So does this make sense to people? All right. Now we're going to define our syntax. And by the way, this is the last slide. So you see the amount of code for doing it when you're using validations. It's actually it's less. It's shorter code. It's a little bit more dense because you're digging deeper into Scala Z functionality. So you know it's sort of different form of complexity, if you will. This right here is actually so if you have like symbol expressions and you have so you just have a symbol and you want to say, okay, I want to read this as an integer, read it as a string. This is how you would do that. And also for any integer expressions, you could actually do addition, subtraction, and division. And literally you can see right here it's a lot simpler. It goes a lot simpler there. And that's how you'd actually define your syntax. So yeah, that's actually a full definition using validations, applicatives as opposed to disjunctions. A good exercise I left folks that you take a look at. It's actually possible not to have the error condition be is like part of your type right here, because the expression is type A to B. You can have it lifted completely in the monad form. So that's like an interesting sort of puzzle to work on. For here, I leave it here just so I think it explains it pretty well. So yeah, I would say to learn more about Scala Z, I would definitely take a look at this guide right here. it's considered by many as authority. There are other tutorials to look at too. I wouldn't jump into this and expect to totally just read through it start to finish and completely get everything that's going on. It's pretty cryptic. Yeah, it's really, I find it good as a reference. And if you combine it with like look at other tutorials and just experimentation, what they call following the types, where you're just exploring the library, trying different operations, and just following the type system. That's a good way to learn Scala Z. CATS, which I referred to before as alternative, that's worth taking a look at. I'd say one of the disadvantages of CATS is, being a relatively new library, it doesn't have everything there that Scala Z has. That could be also an advantage too, because it's a bit more approachable. So you'll find you'll find the essentials in CATS. So it's a good place to start if you want to give that a shot. There's support for something known as Task, Scala Z Task, which we use a lot of this at Verizon actually. And that's sort of a lazy version of a Scala Future. And the Scala Z Task allows you to actually define like an operation, but it doesn't start it right away. You have to manually start it yourself. And being a Scala Z, something that's a part of the Scala Z library, they're very composable. That they're actually a lot more flexible to work with than futures, and very importantly, they're actually safer to deal with. So I don't know if those of you ran into future bombs where you have a future, launch future, and boom, you just got this explosion, your stack's dead. So yeah, I recommend looking at Scala Z tasks. Unfortunately, they're not available to catch yet. I think there's actually work right now to try to pull those out, make them not dependent on the Scala Z library, so you can use them with CATS. Scala Z Stream is amazing. It's a way of doing. It's basically the future of multi-threading, I would argue. As you can do. There's Scala Z Stream process where you define a process in a purely functional way. A signal where you can actually have like values that will actually signal a starting or ending of some condition. Definitely worth taking a look at. And I have to say we are actively looking for Scala, not only Scala developers, but those are working, front, mobile application backend services to large-scale data mining. We have an absolutely awesome culture of learning, working with advanced FP principles, and we have people of all levels of experience, going from new grads to people that have literally written a book on pure functional programming in Scala, literally. So we have the full spectrum, and that creates an awesome dynamic where everybody's, the barriers are down for like teaching and learning new things, and that just elevates everyone into just building just amazing solutions. And yeah, so anybody's interested, definitely talk to me afterwards. Those of you may have seen Go90. Go90 was just released just recently. It's just hot off the press. It's a mobile application for watching videos. A lot of cool features. Go90.com. Take a look. And yeah, that's whoa. Thank you. Thank you. Any questions, anyone? Or yep.
So, having gone through all the slides, can you summarize Kleisli again, if you don't mind, and where are the places where you really use that kind of like closing structure of Kleisli to good effect?
So a Kleisli really simply is a monadic form of a function. So it's a function where you're guaranteeing that the result of the function is a monad of some type. So if you can imagine, that's a powerful guarantee, because it means that you can compose these together using all the rules of monadic composition. So yeah, Kleisli is great if you have functionality that you might want to extend in some way. You want to compose with other functionality. That's why it's naturally I mean, it's just a no-brainer for something like dependency injection, because I mean it's it's a function that's designed for composability, and you can actually just extend it and just lift any function into Kleisli. So you could have a library that's returning a lot of Kleislis, and you could take that Kleisli and say, okay, we're going to map this into something else, and before you know it, you're just mixing in your functionality into this Kleisli. And a really interesting comparison is Kleisli versus free monads. How many of you know what a free monad is? Okay, cool. So, and this is a comparison that I've used, and a lot of folks seem to agree with me on this. It's debatable. Is that a Kleisli can be viewed as a way of, if you're like defining your own language, it's useful like you're building, like say a functional language. Whereas a free monad, you could actually it's purely functional, but you can list or sort of unwrap your piece of functionality so that it has an imperative look to it. So you can say do this step, do this step, do this step. So that's like a good comparison, like where to use Kleisli versus free monad. So yeah, does that answer your question?
Yeah, thanks.
Okay, cool.
So
Yep.
you talked about your scripting language.
Yeah.
That you implemented using Kleisli.
Yes.
Can you shed some more light on how powerful language is, how much code you ended up writing to handle all cases, and how much better was it than if you didn't have one?
So the amount of code for it is not, it's not too bad. I ended up using the disjunction approach in my code. I'm thinking possibly I might convert like maybe parts of it to validation or all at some point. I'm not sure. The disjunctions actually work for my particular case. It'd be kind of complicated to go into how or why it works that way, but that's how I've implemented it. And the type of expressions that I can actually build, they're pretty. I actually have my adapter code that I showed here is actually really simple. It was just for reading a map. I actually have multiple adapter codes where I can actually read things and process data either from like one data format versus another object data format. So I could actually parse the data in a few different ways using these different adapters. So that I'm actually using. The rule-based language I've implemented so far actually has some neat sort of aspects of it. I've actually defined my own closures inside this scripting language, and I use like a double underscore to do that. It sounds scary, but it actually works pretty well. So yeah, it's actually worked really well. I mean, for this code, I mean it's using complicated machinery, but I've had very few bugs to deal with. All the issues I've had to deal with are just external data conversion, because I'm actually interacting with some other code where there's Java code being generated. It's not a library that we wrote in house by any means. It's like something that we just have to use for various reasons. So that's stuff. Those parts I've actually dealt with more bugs with, and is having this thing interface with the external services.
Have you measured performance relative to, say, just like hand coding imperative code or something, like to compare the output?
So, yeah, other folks have done the performance metrics and have found some really impressive results. I mean, there's folks that have compared, they found that Scala Z task, for example, is very performant. People are actually using disjunctions all over the place. You have people using validations and a lot of these features, and I honestly haven't heard of people who have like really shot themselves in the foot with using Scala Z stuff. I mean, I certainly haven't ran into any issues like that by any means. The time that I do run into issues is if I get lazy and say, okay, well, I'm not going to use Scala Z here. It's whenever I decide that, almost every time it's been a mistake. So, okay, that's it. All right, thank you.